Watch what happens to a traditional, centralized message queue when it is subjected to modern, real-time data loads. The infrastructure simply cracks under the pressure. When engineers try to solve this by scaling vertically, adding more memory and processing power to a single machine, they inevitably hit a physical hardware ceiling. Eventually, no single server is large enough to ingest millions of events per second. The logical alternative is to scale horizontally, distributing the data stream across a network of multiple machines. But decentralizing the workload introduces a severe operational risk. Hardware components will inevitably crash, and when a node in a distributed network goes down, the data it holds can be permanently lost. Apache Kafka is a distributed event streaming platform engineered specifically to resolve this tension between scaling for massive throughput and protecting against system failures. It achieves this fault-tolerant scalability through a strictly defined architectural hierarchy consisting of topics, partitions, brokers, and replication. In this series from Royal Research, we are going to reverse engineer a Kafka cluster from first principles to see exactly how these components interact. By understanding this architectural blueprint, engineers can decouple high-volume data ingestion from system fragility, building pipelines that survive inevitable hardware failures. We begin with the most basic organizational unit in Kafka, the topic. You can think of a topic as the specific category or feed name that incoming data streams are routed into. This animation illustrates the internal structure of that topic. It operates strictly as an append-only log. Data cannot be inserted into the middle. New records are only ever added to the absolute end of the sequence. The moment a piece of data locks into that log, it is assigned a unique sequential ID, which Kafka refers to as its offset. This offset enforces strict immutability. Once a record is written to a topic and given its offset, it becomes a permanent part of the history. It can never be altered, updated, or overwritten. Because the records are immutable and the offsets strictly ascend, Kafka maintains a flawless chronological history of every event exactly as it occurred. Before we even introduce multiple servers or networks, this immutable append-only log structure provides the foundational mechanism that ensures data consistency and reliable message delivery. However, a single continuous log creates a severe throughput bottleneck. A single machine can only write to or read from one log so fast before the hardware maxes out. To bypass this limitation, Kafka logically subdivides a single topic into multiple partitions. As shown here, the main stream splits horizontally into 3 separate logs, distributing incoming data evenly. This directly enables parallel processing. Multiple consumers can now read from the same topic simultaneously, processing data from different partitions without locking each other out. The math here is direct. The more partitions a topic has, the more parallel consumers it can support, and the higher the total data throughput of the system. There is a critical engineering caveat to this design. Because the data is split, Kafka only guarantees chronological offset ordering within a specific partition, not globally across the entire topic. By utilizing partitions, Kafka transforms a single sequential choke point into a parallel processing array, solving the horizontal scaling bottleneck. Now that we have subdivided the data logically, we have to look at the physical infrastructure required to house it. In this network topology view, you can see those 3 partitions are enclosed within distinct server nodes. In Kafka, these servers, whether physical or virtual, are called brokers. An entire Kafka cluster is simply a collection of these independent brokers interconnected over a network. The broker acts as the coordinator for its assigned partitions. It receives incoming data from producers, writes it to the disk, and serves read requests to consumers. But mapping partitions to individual brokers exposes a massive vulnerability. If a power failure or network outage takes a single broker offline, the specific partition it holds goes with it, instantly halting data flow. Brokers give Kafka the ability to physically distribute data across a network, but they introduce a catastrophic single point of failure. The cluster requires an additional layer of architecture to survive node crashes. Kafka solves this fragility through a mechanism known as leader-follower replication. When you create a topic, you assign it a replication factor. This dictates how many copies of a partition are distributed across the cluster. Notice how the primary partitions, the leaders, execute automated copying of that data to secondary partitions on entirely different brokers. During normal operation, All read and write requests from clients are routed exclusively to the leader partition. The follower partitions do not handle client traffic. Instead, they asynchronously pull data from the leader in the background, maintaining an exact up-to-date replica of the log. If the hardware hosting a leader partition crashes, the failover sequence begins immediately. The cluster detects the dropped connection and automatically promotes an in-sync follower partition to become the new leader. Client traffic is seamlessly rerouted to the new active node. This replication layer guarantees continuous data availability. It masks catastrophic hardware failures really end user and prevents data loss. There is one final physical constraint to address. Storing an infinite stream of immutable data will eventually exhaust the finite disk space of any broker. Kafka handles this through a log-segmented storage architecture. Instead of one massive file, the continuous partition log is divided into smaller, discrete file segments. Administrators configure specific retention periods. Once a file segment ages past that configured threshold, Kafka safely and systematically purges it from the disk. Kafka also utilizes background data compression, shrinking the byte size of large datasets before they are stored on the broker. Log segmentation and retention policies keep the cluster running. They allow Kafka to sustain massive throughput without triggering cascading out-of-memory failures across the servers. Zooming out from the micromechanics, we can now observe the fully assembled Kafka architecture operating as a cohesive, high-throughput unit. Massive horizontal scalability is achieved by dividing topics into partitions, allowing parallel processing across the network. Fault tolerance is achieved through broker-level replication, ensuring that an up-to-date copy is always ready for automated failover. And absolute data consistency is guaranteed from the ground up because every piece of data is locked into an immutable append-only log. Kafka handles modern, high-volume data streams without data loss because it relies on this highly optimized balance of structural rules. Mastering these principles gives engineers the ability to build resilient, real-time event streaming systems. On behalf of Inside Engine and Royal Research, thank you for watching.